Okay, so this is a continuation of section 9.2. This is part 2. And in this lecture, we're going to look at a different way, another way, a simpler way of determining whether an integer A is a quadratic residue or a quadratic non-residue of an odd prime, where A is relatively prime to P. We know that the Euler's criterion actually provide us one way to evaluate Legendre symbol, which if this is equal to 1, then we know that A is a quadratic residue. If this is equal to -1, then A is a quadratic non-residue of P. So we know that Euler criterion tells us that this one is congruent to A to the power P minus 1 over 2 mod P. So by evaluating this exponent, A to the power P minus 1 over P, and then reduce that mod P, then this is going to give us either a 1 or -1, and then this will determine the what we call the quadratic character of A. However, when P is large, evaluating this exponent, even with repeated squaring, is in itself is going to be computationally challenging. All right, because P, if it is very big, then we cannot reduce very much of the different powers. All right, so Gauss's lemma actually give us a simpler way of determining the quadratic character of an integer A relatively prime to an odd prime P. All right, we're going to give actually two versions of Gauss's lemma that will be of help in determining whether the Legendre symbol give 1 or -1. All right, let me start with stating the lemma. Actually, this is theorem 9.5. However, it is known as Gauss's lemma. All right, and this is the way we usually refer to it more than a theorem. And this is first version of it. And goes like this, the regular setup, let P be an odd prime. A, an integer. Relatively prime. To P if n is the number of integers in this set S, which are multiples of A to A, B, A, and so on, up to B minus 1 over 2A, whose remainder upon dividing the elements in S, elements in the set S, while B exceeds or greater than P over 2. So this is just a P over 2, it's not Legendre symbol, it's just P over 2. So if this is the case, then the Legendre symbol is going to be given as -1 to the n. There's another way we refer to sometimes n. N is also described as the number of least positive residues of the elements in S mod P. Now the word residue here refers actually to remainder, okay? Not the quadratic residue, this is just the remainder, right? We refer to remainders as sometimes also residue. So there are sometimes this language is used, all right, to refer to what the n has. All right, as usual, I'm going to present an example to illustrate actually the method of the proof, okay, of this theorem, all right? So to make it more transparent and help you in understanding the actual proof in general, all right? So we're going to take a prime. I think I'm going to take 11. And you're going to take an integer. I believe it's going to be 7. And we're going to derive basically or go through the derivation of the theorem through this example. Of course, in the particular example, we're going to see some numbers, all right, which easy to see it will satisfy certain properties that we have to show in general. All right, so here's the example. So it's going to serve two purposes. First, actually as an application of the lemma. Second, or more important, is actually to go, actually imitate sort of the proof of the lemma itself. All right? So we're going to let P is equal 11, A is equal 7, which definitely relatively applies to 11. And we need to have this set. Now remember, this set in general is equal to A, 2A, 3A, up to the P minus 1 over 2. And of course, this is equal to 5, right? So we're going to go 3, 4A, and 5A. Which is, in this case, since A is 7, this is going to give us these integers, all right? So this is going to be 7, 2 times 7, 3 times 7, 4 times 7, 5 times 7. And calculating these again is give us 7, 14, 21, 28, and 35. All right, now we're going to define two sets, okay? And that's what we're going to do in the proof, okay? So we define two sets, all right? A, and the elements of this set are the set of remainders. So this one is the set of remainders upon dividing the elements of S by the prime 11. All right? Such that where the remainder is actually less than remainder, I'm going to call them R sub i's, less than P over 2, which is 11 over 2. And you know 11 over 2, it's not an integer, so these Ri, it cannot be equal to 11 over 2. So it's going to be less than or equal, actually, minus 1 means P minus 1 over 2, or 11 minus 1 over 2. All right? And of course, by definition, we have these are bigger than or equal to 1. All right? All right. Now, in this particular case, the A is going to equal to, so we're going to divide these by 11. 7 over 11, it's going to give us actually, the remainder is going to be actually, okay, so we're going to divide, again, each one of these by 11, all right, and we're going to see if the remainder is less than, actually, less than P over 2, and which is, it's going to be 5, less than 5. So, of course, the division goes to 0, and the remainder is going to be 7. So, that's not going to be in this set. 14 divided by 11, and this is going to, the remainder is, actually, let me do the divisions in here. So, we're going to divide 7 by 11, and this is equal 0 plus remainder of, remainder is actually 7, all right? Then we have 14 over 11, which is the same as applying the division algorithm, writing 14 as 11 multiplied by 1 plus 3. So the remainder is 3, so we're going to put the 3 in here. Then we're going to do 21 over 11. So again, write 21 as 11 multiplied by 1 plus, actually, this is going to be 10. Are we going to consider the other remainder from the other set, actually? And then we're going to do 28 over 11. And this means 28 is going to be 11 multiplied by 2 plus 6. All right? And that again is not. And then we have 35. 11 and means 35 is 11 multiplied by 3 plus 2 plus 2. All right, so 2 goes in here. All right, the other set that I'm going to be defining is called the set B, and you guessed it, and this one is going to be the set of remainders upon dividing the elements of S by 11, where the remainder becomes, we're going to denote the remainders in general by S sub i's. So these are S sub I, and I want this is to be actually bigger than P over 2. And of course, it must be less than or equal, the highest it can be is P minus 1. All right? And now the elements of this is going to be the B. I'm going to call this set B. So B in this case consists of those elements, which is the first one is 10. And then we have 7. Actually, the first one is 7 in the order I have it in here. 7, 10, and 6, I believe. All right, so these two sets, we write them down in here. One where the remainder is smaller than P over 2, and the other one, the remainder is larger than P over 2. So we have these two sets. A, which consisted of a 3 and 2, just the remainder, and B, which is 7, 10, and 6. Now, one thing you're going to see that the number of elements in A plus the number of elements in B is, of course, equal to the number of elements in the set S. So this one is equal to the number of elements, which is B minus 1 over 2. In our case, it's going to be 5. So also, they don't have any common element, so we can say that A and B partition actually S mod 11. Because the elements in S actually they are exceeding these numbers, but if we reduce the mod 11, that's what it actually does. So now we're going to define another set, so that when I put them together, it gives me actually S itself. And this set is going to consist of these elements. So now we consider, and this is going to be in general, all right? Consider the set which consists of the remainders of dividing the elements in S by P, all right? And reducing, of course, mod P, means the remainders. And we're going to denote the number of these by M. And then the other one, I'm going to take the elements in B and subtract from B the S1, S2, and so on. And this is, in the theorem, we denoted this, the number of these by N. So there's going to be S sub N. So in our case, this set only consists of 3 and 2, because these are the remainders that are less than P over 2. And this one is going to be 11 minus 7, then 11 minus 10, then 11 minus 6. Okay? So this set is going to be 3, 2, this one is giving me 4, it's going to give me 1, and that's going to give me 5. So these are the same as these elements, because we write them as 1, 2, 3, 4, 5, and 5 is equal 11 minus 1 over 2. Okay? So in the general case, we're going to see that this is going to equal to 1, 2, 3, up to P minus 1 over 2. And basically, of course, in here we see that, okay, doesn't need any proof, but in the general case, we need to prove that this set and this set are actually identical. And a big portion of the proof actually is to prove this. Now, we're going to take the product of these elements in two ways. All right, so we're going to take the product of these and the product in general of what these are equal to, okay? And they're going to be congruent to each other mod, of course, P. All right, In our case, we're going to be considering this set, and we're going to take in the product of these elements, 3 times 2 as is. I want to keep this 11 minus 7, 11 minus 10, and 11 minus 6. All right? I know this is going to be congruent to the product of 1, 2, and so on up to 5. Or up to 5. Okay? And this one is mod 11. Okay, let's look in this side, in here. This one, I can write as 3 times 2. And this one, I can write actually as let me see how I want to actually write this. I know how to write it in the general case, but let me. All right, so we have this one is 3, 2, and this one, when we reduce actually mod 11, it becomes negative 7. All right, and this is negative 10, and this is negative 6. All right, so when I pull the negative out, so I have negative 1 to the number of these, it's going to be 3, and then we have, of course, 2 times 3 times 7 times 10 times actually 6, and this is congruent to 1 times 2, 3, 4, and 5. Also, we have one other thing, that this product, actually, these are congruent to the original elements in S. So I can write this as 2, actually 1 times 7, all right? First of all, we have 7. Then we have multiplied by 2 times 7. Then we have 3 times 7. And then we have 4 times 7. And then 5 times 7. All right? Because these are the remainders. So they, when we reduce mod 11, they give you the same numbers. And this one is 1 times 2, 3, 4, 5 mod 11. All right, so in here, we do have negative 1 to the 3rd, and then we have 7 to the 5th. That's b minus 1 over 2. And then we have the product of 1, 2, 3, 4, and 5. And this is congruent. And this product is 5 factorial mod 11. And also on the other side, we have minus 1 times 5, 7 to the 5th, then 5 factorial. All right, let me write this down. Again, we're going to be repeating this argument in general. And sometimes actually in some of the places, the general case actually is easier to see than the special case, because we get confused with the numbers in here. So then we have negative 1. This is the left side to the 3rd. Then we have 7 to the 5th. Then we have 5 factorial. And then we have also 5 factorial mod 11. Now, since 5 factorial, of course, is relatively prime to 11, all right? Then we can divide both sides by 5 factorial, and then we get this. Congruent to 1 mod 11, almost we're there. Now we're going to multiply this by negative 1 to the 3rd. So we're going to multiply both sides by negative 1 to the 3rd, and then I come up with 7 to the 5th is congruent to negative 1 to the 3rd mod 11. Now remember that the 5 to the 7 to the 5th is actually the Euler's criterion exponent. So this is by Euler criterion. This is 2 by 11, which is equal, sorry, 7 is equal 7 phi p minus 1 over 2, which is 11 minus 1 over 2. This becomes equal 7 to the 5th. And now we are saying that this is what we've shown, all right? This is congruent to negative 1 to the 3rd, which is negative 1 mod 11. And it makes the value of 7 over 11 is actually equal negative 1, all right? So in other words, we could interpret this by saying that 7 is a quadratic non-residue of 11. But since we are doing the proof together with the calculation, it kind of looks very, very hard. But in practice, when we want to just apply Gauss's lemma, all what we need to do is to find that actually the set B, basically how many elements it has, which has 3 elements, and then this gives us what the Legendre symbol will be. All right, now we're going to proceed to the proof of the Gauss's lemma. All right, and I hope you remember the sets that we defined, and then we just need to justify all the properties that we numerically so they satisfy. All right, here's the proof. This is Gauss's so we're going to start with the set S, which consists of A, 2A, 3A, up to B minus 1 over 2 times A. All right? So we're going to say this. Since B is an odd prime, B over 2 is not an integer, hence every residue or we call it remainder upon dividing the elements of S by B is either less than P over 2 or bigger than P over 2. It cannot equal. Equal to P over 2. Because it's not an integer. Always the remainder want them to be integers. All right, now we're going to let A consist of R1, R2, up to Rm. There's the remainders. Upon dividing. again, the elements of S by, since we repeated this several times, by B, all right, where these Ri's are smaller than B over 2, and they are bigger than or equal to 1, all right? And we're going to define the set S B we're going to let B equal S1, S2 up to S sub n. And this n is the same as the n in the lemma itself, all right? So these are the remainder, the set of remainders upon, again, dividing elements in S by P, where the SI's are actually bigger than P over 2, but they must be actually less than or equal to P, P minus 1, or less than P. All right, now we must have the M plus n, like the number of elements in A plus the number of elements in B, actually must equal the elements in S. So this must be the same as the elements in S, which is P minus 1 over 2. All right? Because we are just taking the elements in S and dividing them by B and put, those with the remainder less than P over 2 in A. If the remainder is bigger than P over 2, we put it in B. So they just test partition. Actually, S. All right. Now we're going to consider this set, which is going to combine basically A, and we're going to subtract the elements of B from the elements of B, the SI's, from the prime P. We're going to consider this new set. R1, R2 up to Rm, and P minus S1, P minus S2 up to P minus S sub n. I claim that this set, this new set, now remember all the elements in A are actually is going to be in S, all right? Because the elements of it are actually less than B over 2. These ones, they might actually, the element in S, those are that has remainder that are bigger than P over 2. So we are going to reduce them basically. We're going to subtract them from P, and doing this is going to size them down. Mod P basically. So this is going to be the same as this set. Of course, in a different, the order here is not going to be the same as the order of the set that I'm writing now, as we've seen in the example. But as sets, they are the same. So we want to prove that this, as I said, this is an important claim. Now we're going to do this by saying that every element in the set on the left-hand side is actually an element on the right-hand side. Now, since R sub I, by definition, this one is bigger than or equal to 1, this then actually P over 2. This implies that R sub I less than or equal to P minus 1 over 2. All right, because it's less than, let me actually put the double inequality here to all the inequalities. Okay, so I have 1 less than or equal r sub I, and by definition these are less than p over 2, and this one is less than or equal to p minus 1 over 2. All right? Actually, the other way around. Yeah, this one is less than p minus 1 over 2, less than p over 2. I'm sorry. All right, and this means that the r sub i's does belong to the set. Because each of the elements in here is squeezed in between 1 and p minus 1 over 2. Now, how about the p minus s sub i's? Okay, so that's what we're going to do next, just to show the other elements in this set. P minus Si belongs to this. All right. Now we know that the S sub i's, remember that this one is bigger than P over 2. And the highest this can be is actually P, or less than or equal P minus 1. But let's take this part of the inequality, and I want to multiply it by a negative. So negative Si becomes less than negative P over 2. And let me add P to all sides of this. So we're going to add P. So we get here P minus Si less than P over 2. P minus P over 2 is there. And also we know that this is definitely going to be bigger than or equal to, I really don't care what this one is bigger than or equal to, as far as it is less than that, okay? Definitely is going to be, this is P is bigger than this. I don't care, yeah, just leave it like this. So this implies that P minus Si is also in this set. All right, I know the other side of the inequality in here. We just know that it's going to be this. All right, so this means that we have this inclusion. That the left-hand side now is a subset. All right, so this is contained in here. Next, I want to show that the number of elements in here is the same as the number of elements in there. Now, this is step we don't have to check in the case of the example, because what we got in here are distinct elements. Okay, means the Ri's are all different. The P minus Si's are all different. Now, in here we have to show this, okay? So I'm going to show that all the Ri's are not equal to each other, and the P minus Si's are not equal, and the Ri's and the P minus Si's are not the same. All right? So again, to show Ri does not equal Rj for every I does not equal j between 1 and n. All right, so we have to show this one actually in general. Now we know that Ri actually is of this 4. It came from A multiplied by KR for some KI between 1 and p minus 1 over 2. Right? And then we actually reduce that, then reduce to mod p. That we took the remainder. All right? This is the same as the remainder is going to make this reduced this way. So let's assume that actually we have the actually I want to show that these are not congruent to each other, mod p. Okay, so these are mod p. And the I and the j are between 1 and p minus 1 over 2. All right, so let's assume that they are, in other words, we have the AKI. Actually, what in here equal, but we need to reduce them when we're talking about the k sub i's. A sub k, these are actually not equal to each other. Okay, for I does not equal to j between 1 and p minus 1 over 2. So these are coming from actually doing this mod p. I'm sorry. So the r sub I is equal k sub I mod p. So let's assume that we have the a sub I is actually congruent to another one, which is the r sub j, which is coming up from a times k sub j. All right, mod p. So let's assume that these are actually congruent to each other, which means that Ri is equal to the R sub I is equal to the R sub j. Well, this implies that P is going to be divisible by A times Ki minus Kj. But since the greatest common divisor of A and B is equal to 1, this implies that P divides the difference in the k sub I minus k sub j. This is Euclid's lemma. All right. Now, but this is not possible, okay, since this is impossible. Since these k sub I and k sub j bigger than or equal to 1 less than p minus 1 over 2. So when you take their difference, it cannot be actually divisible unless this is impossible, since this unless ki is equal to kj. But again, which means this implies that the actually the Ri is gonna equal to Rj, which is a contradiction. All right? Or unless they are equal, then which implies they must equal, they cannot be not equal to each other. All right. Similarly, we can do it for the S, P minus S sub I. Very, very similar argument. that the B minus SI does not equal to B minus S sub J if I does not equal to J. One other thing we need to show, which I'm going to actually show also because it's slightly different, and that is this. So the R sub I and B minus S sub J's are distinct. Again, let's assume that we have the R sub I is congruent to A K sub I mod B, or coming from this multiple by reducing it mod B, and the B minus Sj is actually coming from the same thing. It's going to be K sub J times R mod B. Where the Ki and the Kj again are between 1 and B minus 1 over. But if we have these are equal to each other, minus B minus Sj, this implies that the originals, which are multiples of A, is going to be congruent to A K sub J mod B. Same as before, which produces this congruence relation. So this implies that P is going to divide the difference A K sub J, which is equal to A K sub I minus K sub J. And again, since P is relatively prime to A, the P must divide the difference. And again, which makes this is not possible, all right? Because again, we have actually in this case, we have these are going to be the sum of these, because in here, this becomes actually negative Sj, all right? So this becomes negative in here. We get these to be positive, and this is positive, positive. Again, which is this one is now remember the top Ki K sub J is between P minus 1 over 2. This is 1. So when we add them up, we're going to come up with Ki plus Kj, and this is going to be less than or equal to P minus 1. So you cannot have this is going to be larger than P when the sum is actually smaller than P minus 1. So this is not possible. This is not possible. So the only way this means, this implies that Ri cannot equal B minus Sj for any I and j. This time, we cannot have these all equal to each other because actually their number is different. All right, but for different i's and j's, they cannot be equal to each other. All right, now, what we have accomplished, we have this set, which is R1, R2, up to Rm, then B minus S1, B plus S2, up to B minus Sn, has M plus N, all right, elements. And this is equal. And this number, which is M plus N, is equal P minus 1 over 2. The original elements in S. Remember, S is A, 1A, 2A, up to P minus 1 over 2A. So this one has P minus 1 over 2 elements. All right? And we showed that this one is a subset. In the first part of the proof, we showed this is a subset of 1, 2, up to P minus 1 over 2. But both of these have the same number of elements. This one has P minus 1 over 2 elements. Well, if one is a subset of the other and they have the same number of elements, well, they better be equal to each other. So therefore, they are equal as sets. So in other words, we did not show that the 1 up to P minus 1, every element in here is contained in here. We used a different argument, a different way to show or force the equality between the sets, because these are finite, by comparing the number of elements. Showing one is a subset of the other, and the number of elements are the same, which make the sets are equal. Now we need to multiply them, all right? And in here, actually, the argument becomes easier to see than with the numbers, okay? In the example, so that we have to artificially, basically, bring things in to make it the same. All right, well, in here, it's going to become natural. Well, in some sense, all right? Now, we have, since the two sets, which is R1 up to Rm, P minus S1, P minus S2, P minus Sn. We know this is equal to this. Then the product of the elements in here equal to the products in here. Well, let's write the product in here, which is R1, R2, up to Rm, and then B minus S1, B minus S2, up to P minus Sn, is equal to this product. And here we have equality. All right? Now, we're going to actually do now mod. Okay? So we're going to take mod P. Now, we know that P minus Si is congruent to negative Si mod P. Of course, the P that appears in front is 0 as far as mod P is concerned. So then we can write this actually as R1, R2, up to, then we have a negative, and how many negatives we're going to have from the side is negative 1 to the n, then S1, we put this is Rm in here, then this is S1, S2, up to Sn, And now we have to use congruent. And we're going to have, again, this one is p minus 1 over 2 factorial. But now we're going to put mod p. Because the left-hand side, we reduce it mod p. But yeah, I didn't do anything to the right-hand side. All right, now all together, we have the Ri's, Rm, and the S. These are actually, again, are the same as or equal to or congruent to A times 2A times 3A up to P minus 1 over 2A mod P. Right, because these are the remainders. Now I want to replace the R's and the S's by the product of the A to A and so on. All right? We're getting there. It's almost done. So this implies that this equation right here, or this congruence relation, it becomes a, let me pull out the -1 in the front to the n, and the r's and the s's multiplied together. I'm going to replace them by a times 2a times 3a times b minus 1 over 2a, and this is congruent to b minus 1 over 2 factorial mod p. Again, in here we're going to take a as a common factor, so it becomes minus 1 a. There are p minus 1 over 2 of them. And then the multiples of the a is 1, 2, 3, up to p minus 1 over 2 factorial mod. Also, this product of 1, 2, up to p minus 1 is also p minus 1 over 2 factorial. So the left side, we need an n in here, sorry. So this is n, and this is p minus 1 over 2, and this is p minus 1 over 2 factorial, congruent to p minus 1 over 2 factorial mod. Now, the greatest common divisor of p and p minus 1 over 2 is equal to what? Actually, factorial. This one factorial. This one is equal to 1. Because p does not appear in any one of the numbers in this factorial. Because it's going to start with p minus 1 over 2, which is actually smaller than p. All right? And which means we can divide. So we can divide by this, and this implies minus 1 to the n a for p minus 1 over 2 is congruent to 1 on p. And now we can multiply both sides of this by minus 1 to the n. So in the left side, it becomes minus 1 to the 2n, which is always equal 1. And on the right side, it's going to be there. Minus 1 to the n mod p. Finally, we're going to bring in Euler's criterion. By Euler's criterion, the left side mod p is equal the Legendre symbol by Euler criterions. And we have A by B is congruent to A or B minus 1 over 2, which is congruent to minus 1 to the n mod B. Again, we use this argument again. There is a congruence relationship, but this one is going to be equal plus minus 1, and very far right, or this equal plus minus 1. Then either these are actually congruent mod B, but they cannot actually, they must equal. All right, they must equal to each other. So this implies A by B is in fact equal. Right, because if they are not equal, it means one of them is positive 1 and the other negative 1, and being congruent mod B leads to a contradiction. It means B is going to be divisible by 2, but B is an odd prime, so that they must actually equal to each other. All right. Next, we're going to look at some applications. Or Gauss's lemma. This is actually a long section in here. So probably I want to again do maybe another lecture, but I want to be given some applications first. All right. I'm going to go fill up some water in here. Let me stop this. All right. So we're going to look at some of the applications of Gauss's lemma. Here, applications. Gauss's remember the two fundamental problems of the quadratic residue theory. One is to calculate whether an integer, A, relatively prime to another prime, is quadratic residue or quadratic non-residue. And now we have, of course, Gauss's lemma actually tell us by calculating the numbers of remainders in this set S, which is A, 2A, and so on, that are larger than P over 2, and then we take the negative 1 to the end. If that's going to be positive, then yes, it is, A is a quadratic residue. If it is negative, it's a quadratic non-residue. Or we could use, of course, Euler's criterion. The second problem was, is given, A, an integer A, and we need to find all primes, all odd primes, such that A is a quadratic residue of P, and all primes such that A is a quadratic non-residue. Non-residue of really this is equivalent to find all P's such that 2 over P is 1 or negative 1. In other words, for what primes P is going to get 1, and for what primes we're going to get negative 1. All right? So we're going to classify those primes that give me 1 and those they're going to give me minus 1. And this is the first application we're going to have for Gauss's lemma. Is actually, sorry, not for 2. We're going to do it for 2, but for A. All right? Now, we're going to give a solution for this. Okay, so the next theorem solve this problem for A equal to. All right, we already have actually the solution. This is in theorem 9.2, the very first or the second theorem, or first theorem in this section, 9.2, is it is done for A equal 1 and negative 1 if you go back. So now we're going to do it for 2. So this is, remember, this is the second, all right, problem. Second fundamental problem in residue theory. All right, well, let me state the theorem. They actually give us what the 2 over B when it is equal 1 and when it is equal negative 1. Now we're going to see this is very, very, very crucial. All right, when we introduce the quadratic reciprocity law, because it's going to be a fundamental step toward doing calculations with Legendre symbol. All right, so this is theorem 9.6. Again, if E is an odd prime, then 2, the Legendre symbol is equal 1 if P is congruent to 1 mod 8 or P is congruent to 7 mod 8. So another one of the primes of the form 8k plus 1 and 8k plus 7, all right, is gonna be 2 is a quadratic residue of these primes. And it's going to be negative 1 for the other primes if P is congruent to 3 mod 8 or P is congruent to 5 mod 8. Now remember the other mod numbers, which is mod 2, P mod 2, these are actually even numbers, and then mod 4, also even numbers, 6 and 6 and 0, of course, are going to be all even. So these are the only odd, all right, and not each one of these is a prime, but whenever it's a prime of this form, all right, so this is very important. All right, so this is the kind of what we're looking for in solving the second problem. All right. All right, now here's the proof of this. Now remember by Gauss's lemma, we have 2 by P is equal minus 1 to the n, where n is the number of remainders or the number of numbers, the number of elements in this set, which consists of 1 times 2, because my A is 2, 2 times 2 2 times the 3, and so on, up to, actually let me write this, well, I need more space for this. Let me write it in here. For this set S, it's going to be 2 times 1, or 1 times 2. Let me put the 2 in the back. All right, this is A, 2A, and so on. Remember that the way we did. So 2 times 2, then the 3 times 2, up to P minus 1 over 2 times 2. And this last product is actually P minus 2. Minus 1, sorry, P minus 1. All right, so this is the number of elements in here whose remainder upon dividing by P is bigger than P over 2. Upon dividing by P is greater than or exceeds P over 2. Now, since all the numbers in S actually are less than P over 2, since all the elements in S, because remember that the highest element here is P minus 1, right? Since all the elements in S are less than or P, the remainders of dividing each element in S, each element in S are the same as the elements of S. Now, of course, when you get a divide, you're going to come up with, division equal to 0, and the remainder is going to be either one of these, depending which one we are dividing by. All right? So this is a special situation, basically, because we are taking multiples of 2, and the last element is a P minus 1 over 2. Multiple of 2 is just P minus 1. So what we need to do, we only need to know which one of these elements actually bigger than P over 2. So we only need so this implies we only need to find how many elements in S are greater than P over 2. All right, to give us N. N is the number of elements supposed to be a remainder, but since the remainder are the same as the elements in S, just the one greater than P over 2. And to do that, what we're going to do, we're going to find the number of elements that are less than, all right? And we're going to subtract that out from the total number of elements, okay? So the strategy is going to go like this. So first, we find the number of elements in S that are less than E over 2. Now we wrote the elements of in the proof of the Gauss's lemma, the elements of B. Okay, so how many of them are there? Now, so that is going to go like this for 1 less than or equal. These are multiples of 2 for than or equal k less than, or actually less than or equal b minus 1 over 2, or less than b over 2. 2k, we have 2k, because on one multiple of this by 2 is going to be less than d over 2 if and only if k itself is going to be less than p over 4. Okay? So this one is going to be less than p over 4. All right. Now let's use the greatest integer function to come up with actually a count for this number. Remember that if this bracket is the greatest integer function, then there are p over 4, all right, integers in S less than p over 2, right? Because the k must be less than or equal, so the multiples of these could be less than or equal to 2. Then this one, which is the largest integer, smaller than or equal to p over 2, and that's what this exact number is. All right? All right, now, therefore, the total number of elements in S is p minus 1 over 2. Okay? Or actually, not the, therefore. This is another statement. Now we need to come up with the number that are bigger than p over 2. So in S, and now we're going to put that this implies that the total number of elements in S greater than p over 2. Remember, this is n, that is n. Is given by this. The number of elements in S, which is p minus 1 over 2, minus the one which are bigger than p over 2. And that one is given p over 4. All right, well, now the proof of the theorem is going to follow just by doing basic arithmetic. Okay, so remember that we have 4 cases. We're going to let p congruent to 1 mod A. This implies that p is equal 8k plus 1. And let's calculate what is the n for this. It's going to be 8k plus 1, that's p, minus 1 over 2, minus the greatest integer for 8k plus 1 over 4. The first term, the 1 negative 1 cancel out, so you get 8a over 2, that's 4k. Minus, now upon dividing this greatest, we're going to come up with 2k plus 1/4. But 2k is an integer, 1/4 is the fractional part, so this gives me 4k. So this is equal 4k minus 2k. And this gives me 2k. So I'm going to come up with an even number. Now then we have, therefore, Legendre symbol for this, as the theorem is saying, is going to be equal minus 1 to the 2k, and this is equal positive 1. All right? So if p is of the form is congruent to 1 mod 8, it's going to give me positive 1. I want to leave the case when this one is congruent to 7 mod 8 to also show this is 1. And then I want to do the second type where we have quadratic non-residue. So I want to do the 3 and leave the 5 for you. So really the crucial proof in this is just finding this n, all right? That's the whole idea about Gauss's lemma. All right, now if k is congruent to 3 mod 8, remember the 2 by p is going to be equal negative 1. So in this case, the k, the p, not k, that's not it. Okay, then p is equal 8k plus 3 plus the 3, and the n, which is going to be, remember what the n in here is equal p minus 1 over 2 minus bracket p over 4. So 8k plus 3 minus 1 over 2 minus 8k plus 3 over 4. Okay, so this is equal 8k plus 2 over 2, and the bracket is going to be 2k plus the 3 over 4. And the 3 over 4 is less than 1, so this means, again, we're going to come up with this is 4k plus 1 minus 2k. All right, and this is going to be 2k plus 1. And this is up. So then, Legendre symbol for this case is going to be 2k plus 1, and this is minus 1. And again, this agrees with the theorem for p congruent to 3. P congruent to 5 also is going to, this calculation is going to give you an odd integer. When you raise it to the negative 1, to that odd integer, you come up with negative 1 again. All right? All right, here's another application. Actually, the corollary to all of this, which makes it even easier to remember this Legendre symbol for 2 by p. Okay, corollary. Two by p is equal negative 1 p squared minus 1 over 8. All right? Oh, that's not bad. This is very, very simple. Okay, let's see the proof of this. And the proof of this is actually, we know that this integer, this is going to be plus minus 1. So I want to show that It gives me +1 if P is congruent to 1 mod A, or P is congruent to 7 mod A. And it's going to give me -1 if P is congruent to 3 or 5 mod A. All right? And really the idea is just the same as we did in the previous theorem. It's just to take the different cases. All right? So I will take one case of each. All right? And check that actually this is going to give us the correct parity, means +1 or -1. So if P is congruent to 1 mod A, it makes P equal 8K plus 1. And let's look at what P squared minus 1 over A is going to be equal to. 8K plus 1 squared minus 1 over A. And this is just basic calculations. 16K plus 1 minus 1 over A. And you can see we're going to come up with an even integer. So this one is going to give me 8K plus 2K, and this is 4K plus K. So this is even. And yes, when you take -1 to the P squared minus 8 over 2, you come up with +1. And similarly to the other cases, I was going to do one from here. I think that, as you can see, the calculations are so straightforward, there is no need to do this. All right, so this is this. The good thing about this is easier to remember instead of all these cases there. So just plug in the double prime, and whatever it gives you, it will be positive or negative. But the different types of primes, sometimes we need them, just the form, in some proofs we need what type of prime is it. Means it's not going to solve all our problems, basically. Let me see it here. Okay, I'm going to skip one theorem in here. I will come back to it on actually the. It looks like I'm going to do another lecture over this on debating. Yeah, well, I'm going to do another lecture on this. Let me do theorem 9.8, and then I will come back and do 9.7. Because this is a little more straightforward. With the time, I'm going to put in this. Now we're going to show there are infinite limit primes. We've seen these type of theorems and proofs many times. There are infinitely many primes of the form (8k minus 1). And by the way, this is equivalent to, all right, this is the same as 8k plus 7. In both of these, this is the prime P is congruent to either -1 or 7, because these are both mod A. I want to describe it in terms of mod P. congruent to -1 mod 8 is the same, is the same primes as P congruent to 7, because -1 is congruent to 7 mod 8, all right? Or if you're in the form 4K or 8K plus minus some number, this one or this one are the same. So in the book it is stated this way. Now remember all these types of theorems which concern, there are infinitely many primes of a certain form. There are special cases of this very, very important theorem by Dirichlet, which he said that there are infinitely many primes in a progression sequence, all right, which actually these satisfy that. The problem is, we cannot prove Dirichlet theorem because it is very, advanced theorem. It uses theory of functions to complex variables, all right, to prove. So that's why we have all these little pieces that we can do using basic, number theoretic results that we already proved. All right. So here's the proof, and the proof goes similarly. We assume there are finitely many. Okay, assume that there are finitely many primes of this form. K minus 1. Let's call them, say, P1, P2, up to P sub R. All right? Actually, equal here. This is n. We're going to then define a number. Let n equal 4, P1, P2, up to Pn. And we're going to do this one minus square minus. Now, it's not very hard again to see that this number is actually of the form 4K minus 1, 8K minus 1. When you square this, you could factor out an 8 and then rearrange it and have a -1. All right? I'm trying to regard this all. Now, by the fundamental theorem of, again, this is actually, I want to take this as capital N, not small. All right? By the fundamental theorem of arithmetic, again, this number is, in fact, this is odd. And to see this, all we have to do is actually get this one squared. And you can factor a 2 out. And then we have, this one is 8, P1, P2, up to Pn squared, minus, actually, let's see here, 8 times this, minus 1. Well, actually, this one is, and this one is odd, okay? So this is odd. All right. So and then it has 2, and then the other part of it is odd. So this, by the fundamental theorem of arithmetic, n must have an odd prime factor. Let's say, again, I don't know what type of prime factor is this, but we know that it must have one. Because n is not a prime itself, so it is 2 times an odd number, and also I can actually, yeah, that's just that's what I need here. So let's now look at some divisibility relation, and we're going to lead to a contradiction. Right, so we have P divides N, and this is equivalent to saying that N is congruent to 0 mod P. And I could also write this congruence relation as the 4 P1, P2 up to Pn squared is congruent to 2 mod P. Because we could write N like this. And this means that this equation 2 is a quadratic residue of P. Because since x equal to this number for P1, P2, it's a legitimate number, once we say this is a solution to x squared congruent to 2 mod P. But really, this is satisfy this equation. But from the previous theorem, that is actually theorem 9.8, 6, 9.6. All right, we had 2 by P is equal to 1 because it's a quadratic residue. All right, 2 is a quadratic residue, so this one is equal to 1. Now let's look at the type of P that give me 1. So again, from the same theorem, this implies that P is congruent to 1 mod 8, or P is congruent to 7, which as they say, this is also congruent to negative 1 mod 8. Now, if all prime factors now remember that we have P is a prime factor of N. Now if all prime factors of N are of this form, k plus 1, then N is of the same form. Is of the same form. All that you have to do in here is take a product of, just to show this, if you take a product of any two numbers of this form, 8L, let me call K prime, plus 1, then it's not very hard to see that when you multiply this, you get 64 K prime plus 8K plus 8K prime plus 1. And you could factor an 8 out of this plus 1. So you get it of the same form, but n is a, if it is all the prime factors, then any two of them is going to give you the same, so all of them is going to give you also the same form. But definitely, the n itself is not of this form, but n, which is equal to this, squared minus 2, this one is not of the form uh, 8K plus 1. All right? Actually, we just say that it is actually of the form 8K minus 1. K prime minus 1. So n of this form. What does this mean? This means that actually the P, all right, therefore n must have a prime divisor of the form 8K minus 1, which is the same as 8K plus 7 minus 1. And this means that the P itself must equal a piece of I for some I between 1 and n. It's going to be one of those piece of i's, okay, which form a complete list of all the primes of the form for 8K minus 1. Now what we have the situation that P, which is equal P sub I, divides n, all right? And of course, P sub I divides the product of all these squared, okay? And in that combination of these, which is going to give us a difference of, to be 2. So this implies P sub I is going to divide, all right, n minus these, 4, P1 up to P2. Actually, let me put this one in front. So I get 2 instead of negative 2. So 4, P1, P2, Pn squared minus n. And this is equal 4, P1, Pn squared minus the same thing, plus, all right? So these cancel out and we get 2. So Pi divides 2. And this is contradiction because all the Pi's are actually are odd. Okay, since all the Pi's are odd. Because of the form 8K minus 1. Okay, so it is odd. But so this is a contradiction, therefore there are infinitely many primes. Infinitely many primes of the form 8k minus 1, equivalently 8k plus 7. Okay. All right. All right. There are a few other results left. Probably going to take a little bit of time. Among these, we're going to look at another version of Gauss's lemma, which actually going to make it even easier to find the quadratic character of a certain integer, means find what is the Legendre symbol for A by B. And then also one other application of Gauss's lemma. It's not going to be very long, but I prefer to do it some other time. Or I'm going to stop writing.